Namaste, my friend. Welcome back to JEE Physics with Typical Monk. This is class 2, and today we finally set things in motion. Literally, every object that moves has a position, a velocity, and an acceleration. And in JEE Physics, all three are tied together by one idea: calculus. Position tells you where. Velocity is how fast that position is changing. Acceleration is how fast the velocity itself is changing. David once used the formula v equal u plus a t on a problem where the acceleration was doubling every second, and he got the wrong answer because that formula only works when acceleration stays constant. Today, we build motion the honest way, from derivatives and integrals. So you never make David's mistake again. Take a slow breath. Let us begin. So what will you carry home from today's class? First, position, displacement, velocity, and acceleration. Second, how motion is rebuilt by integration. Displacement as the integral of velocity. Velocity as the integral of acceleration. Third, the equations of motion, derived by calculus, not just memorized, and exactly when they are allowed to be used. Fourth, free fall as simply one more case of constant acceleration. And fifth, reading and building xt, vt, and a graphs, where slope means derivative and area means integral. Ready? One idea at a time. Let us start at the foundation. The four ideas everything today is built from. Position is where a particle sits on a line at a given time. Displacement is the change in position, a vector, while distance is the full length traveled, always positive. Velocity is the derivative of position with respect to time, b equal dx dt, the slope of the xd graph at that exact instant. Acceleration is the derivative of velocity with respect to time, a equal dv dt, the slope of the vt graph. It also equals v dv over dx, which becomes the hero the moment acceleration depends on position instead of time. And going backward, we recover motion by integration. Position equals the integral of velocity. Velocity equals the integral of acceleration. Differentiate to go down this chain. Integrate to climb back up. Look at these three graphs stacked together, because G loves to test exactly this picture. On top, the position time graph. Wherever this curve is steep, the particle is moving fast. The slope at any instant is the velocity. In the middle, the velocity time graph. Because our acceleration here is constant, this line is straight, and its own slope gives the acceleration. The shaded region under the velocity time graph up to any instant is the displacement up to that instant, literally the integral of velocity over time. And the shaded region under the acceleration time graph is the change in velocity, the integral of acceleration over time. Slope steps you down from position to velocity to acceleration, area climbs you back up. Now let us derive the three equations of motion properly, the G way, using calculus instead of memorizing them. Start with acceleration constant, call it A. Integrate A with respect to time from 0 to t, and velocity becomes u plus a t. The first equation is born, not quoted. Now integrate this velocity with respect to time, and position becomes the starting position plus ut plus 1/2 a t squared, the second equation. Combine the two, replace time using the first equation, and you reach v squared equal u squared plus 2a into displacement, the third equation with no time inside. Free fall is nothing new. Just set acceleration equal to g downward. But remember the fine print. The moment acceleration itself depends on time or on position. All three of these break down, and you must return to direct integration. Time for a full G numerical, the monk's way, slowly. A particle starts with velocity 3 meters per second, and its acceleration is given by A equal kt, with k equal 2 meters per second cubed. Find its velocity and its position at time equal 3 seconds, starting from position 0. Step 1. Given initial velocity 3 meters per second, initial position 0, and acceleration are equal to t in c units. Step 2. Integrate acceleration once for velocity. Velocity equals 3 plus the integral of 2t dt from 0 to t, which gives 3 plus t squared. Step 3. velocity at 3 seconds. 3 plus 3 squared, that is 3 plus 9, giving 12 meters per second. Step 4. Integrate velocity once for position. Position equals the integral of 3 plus t squared dt from 0 to t, which gives 3t plus t cubed over 3. Step 5. Position at 3 seconds. 3 times 3 plus 27 over 3, that is 9 plus 9, giving 18 meters. Notice the pattern. Integrate once for velocity, integrate again for position, that is the entire method. Every single time acceleration is given as a function of time. Now the two situations G actually tests side by side. On the left, acceleration given as a function of time, like the one we just solved. Integrate it once, you get velocity as a function of time. Integrate again, you get position as a function of time. Simple in principle, however messy the algebra. On the right, acceleration given as a function of position instead, and this is where most students freeze. The trick is v dv over dx equals a direct consequence of the chain rule, and you integrate over position, not time. Notice that suv itself is just the laziest special case, where acceleration is a plain constant number. Integrating it is trivial, and that triviality is exactly why those three equations exist. The moment you see acceleration written as a function of t or of x, resist Savat completely and reach for the derivative or the v dv over dx relation instead. Now sit up straight. 5 lines that decide G numericals on this topic every single year. 1. Velocity is the slope of the xt graph. Acceleration is the slope of the vt graph. Read the picture as calculus, not as arithmetic. 2. The area under a vt graph is displacement. The area under an 8th graph is the change in velocity. Always signed, never automatically positive. 3. Whenever acceleration is handed to you as a function of position, reach immediately for v dv over dx equal a. 4. The 3 Savat equations are valid only for constant acceleration. The instant it varies with time or position, you must integrate from scratch. 5. Free fall is not a separate topic, it is the same constant acceleration motion with the equal to g, pointing down. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. The slope of the position time graph at any instant gives the instantaneous velocity. Reason. Velocity is defined as the rate of change of position with respect to time. Is the assertion true? Yes. Is the reason true? Yes. And does the reason explain the assertion perfectly? It does. That is the definition itself. Both true. Reason explains. Option A. Second one. Assertion. The area under a velocity time graph between 2 instants always equals the displacement in that interval. Reason. Displacement is a vector, while distance is a scalar. Both statements are individually true. But pause. Does the reason explain the assertion? No. The area equals displacement because it is the time integral of velocity, nothing to do with the vector-scalar distinction. Both true. Reason does not explain. Option B. Third one. Assertion. For a particle with acceleration I equal kt, the plane formula v equal u plus a t gives a correct velocity at time t. Reason. The formula v equal u plus at comes from integrating a constant acceleration over time. Check the reason first. Completely true. That is exactly its derivation. Now the assertion. False, because here acceleration is not constant, so that plane formula cannot be used at all. Assertion false. Reason true. Option D. A quick match now. Say each relation aloud before I reveal it. Velocity, the derivative of position with respect to time. Acceleration, the derivative of velocity with respect to time. Displacement, when velocity is known as a function of time. The integral of velocity with respect to time. And acceleration, when it is known as a function of position, b times d over dx. If all 4 came to you before the reveal, This calculus is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The slope of a velocity time graph gives the acceleration. Hold your verdict. Statement 2. The three surveyed equations can be used even when acceleration changes with time. Statement 3. The area under an acceleration time graph gives the change in velocity. So, how many are correct? Two statements. The first and the third. Slope of Vt truly is acceleration and area under A truly is the change in velocity. But the second one falls completely. Suvat demands constant acceleration, nothing less. Two correct, and the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. Distance and displacement are always the same number, just different names for the same thing. The truth: distance is the total length of the path traveled, always positive. Displacement is the straight line change in position, and it can even be zero while distance is large, like a particle that goes and comes back. Myth 2. The equations V equal U plus a t, and the other two, Suvat equations, work for any motion at all. The truth: they work only when acceleration is a true constant. The instant acceleration is a function of time or of position. You must integrate directly. Suvat quietly gives a wrong answer without ever telling you it failed. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. If position x equal 3t squared minus 2t in c units, what is the velocity at t equal 2 seconds? Differentiate once, 6t minus 2, so at t equal to 10 meters per second. Question 2. For that same x of t, what is the acceleration? Differentiate the velocity once more, a flat 6 meters per second squared, since velocity was a straight line in time. Question 3. A particle has velocity v equal 4t. What is its displacement between t equal 1 second and t equal 3 seconds? Integrate v2t squared, evaluated from 1 to 3, gives 18 minus 2, that is 16 meters. Question 4. A stone is dropped from rest and falls freely with g equal 10 meters per second squared. What is its speed after 4 seconds? Just v equal gt, 40 meters per second. And question 5. The thinker. A particle starts from rest at x equals 0 and its acceleration is a constant 2 meters per second squared, but this time treated through vdv over dx equal a. What is its speed at x equal 9 meters? Integrate b squared over 2 equal ax, so v squared equal 36, giving 6 meters per second. Exactly what Suvat would also give, because here acceleration truly is constant. Let us gather the whole class in one slow breath. Velocity is the derivative of position, the slope of the xt graph. Acceleration is the derivative of velocity, the slope of the vt graph, and also vdv over dx when position is the variable in play. Displacement comes back by integrating velocity, velocity comes back by integrating acceleration, area under the curve. Every time, the three Suvat equations are calculus in disguise, valid only when acceleration is truly constant. Free fall is simply that same constant acceleration with the equal to g. And next class, we step into two dimensions. Kinematics 2, vectors and projectile motion. The same derivatives and integrals, now with the direction attached to every quantity. Do not miss it. And so, my friend, motion has stopped being mysterious. Every position, every velocity, every acceleration you will ever meet in G is just a derivative or an integral away from the other two. Sarah, David, Lisa, and John all once tried to force Suvat onto a problem where it did not belong. Do not let that be you. Tonight, revise the one line that matters most. V equal dx dt, I equal db dt, and displacement will back up by integration. One idea at a time, you will crack G. Of this, I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in 2 dimensions.